Hi guys, this is a calculus video and um, you're going to want to, so this is video 5-11 to be watched Tuesday, January 17th, and you want to go look at your email right now because I emailed this page to you. So if you have not printed this yet, then stop this and print it. And there is a corresponding homework problem. I think there's one or maybe two, but also see your email. I sent you an email that has the notes pages for videos 5-11, 5-12, and their corresponding homeworks. Okay, so whenever you are given a function, so this is accumulation functions and particle motion. Whenever you are given a function that represents the rate of change or the derivative of another function, write down the following information. Now, actually, guys, for this example, I'm gonna change this f prime to a v, but only so change that to a v, please. Stands for velocity. And then over here also, okay, change that f prime to a v. Leave this stuff over here, but all right. So these are three things that we're going to want to know and be able to use. Displacement, otherwise known as sometimes called net change, is when you're not dealing with a velocity acceleration sort of problem, it's called net change. But this would be, all right, for our purposes today, this is the distance from the initial position. So when you're dealing with particle motion, then this net change is called displacement, and it is the distance from the initial position. Okay, and what it is, the way that you can find it, guys, is you could do the area under the curve or the integral from a to b of the velocity function, and that will give you the displacement, the distance from the initial position. Now that is different than the total distance traveled. For the total distance traveled, you have to do the integral from a to b of the absolute value of the velocity function. And this last thing is if you want an antiderivative, so suppose that you know the derivative function or the rate of change function for something, and you want the antiderivative, then it can be found using this formula here. So f of t, which is the antiderivative that we'd be looking for, is equal to f of a plus the integral from a to t of the derivative function that you would know. And notice how the input to this function, this is called an accumulation function because it gives you the accumulation of whatever is changing over a certain interval. And notice the input is t. The input of this function goes up there in the upper limit. And it's important that this variable is not the same as these variables here. Okay, so we're going to do two examples. Example number 1. An object moves on a vertical line in the time interval 0 to 16 seconds such that its acceleration is a of t equals radical t in feet per second per second. And we know that at time t equals 0, the velocity is negative 18. All right, so yeah, so there's that. All right, so part A, find a formula for the velocity of the object at any time t. Well, guys, to find the velocity, we've got the derivative of velocity, which is acceleration. So we want the antiderivative of this, knowing this information here. So of these three things up here, I'm going to be using this antiderivative formula. So let me write it down. How did I do this earlier? Okay, so f of t, the antiderivative that I'm looking for is actually the velocity function. So I'm going to say, let me just write down the formula. So instead of f, I'm using v. So I'm looking for the velocity function plus the integral from a to t of v prime of x dx. Okay. And let me just fix my papers. So this, guys, v prime of x, that is the acceleration function. So maybe up here we should say that that's, or that v prime. So that's v prime. Okay, so v of t is equal to, in this case, we're working on this interval 0 to 16, and we know v of 0. So this is going to be v of 0 plus the integral from 0 to t. And v prime is, v prime of x will be radical x, okay, because v prime of t is radical t. So I'll just go, and let me write it as x to the 1/2. Okay, so just like that. So I just took this and plugged it in for v prime. But I wanted my independent variable inside here to be x. Okay, so v of 0 I know is negative 18. Plus, I'm going to have to use the fundamental theorem of calculus here. So let's do this without a calculator. So, well, I couldn't use one anyway because that's a variable. So I'm just setting up this bracket, and what goes inside of it is the antiderivative of this. So the antiderivative of x to the 1/2, I have to add 1 to the exponent and then divide by it. So I'll end up with 3/2 as my new exponent, but dividing by it will give me 2/3 x to the 3/2. Okay, and this is equal to negative 18, I just carried that over, plus the way that this notation works is I plug in t, so 2/3 t to the 3/2, and then I subtract what I get after plugging in 0. So 2/3 0 to the 3/2. Okay, so that's just 0. So I'll say this, I'll say therefore v of t equals 2/3 t to the 3/2 minus 18. Okay? All right, so there's that. And now part B, set up an integral to find the displacement in the time interval 0 to 16 seconds. And then we're going to use our calculator to evaluate the integral. Well, guys, displacement is, it's this formula right here. So I need the integral from a to b, in this case a is 0, b is 16, of the velocity function, which I found here. Okay, so that's the velocity function. So 2/3 t to the 3/2 minus 18 dt. And then it said I could use my calculator, so I'm going to use Math 9. So I go here, and I go Math 9, 0 to 16, 2/3 x to the 3/2 minus 18 with respect to x. Okay, so this is the displacement at the end of the interval. And let me just, okay, so we've got a vertical, just for a visual. We've got this vertical path, all right, and vertical number line. So let's say that that's 0. And then let's say that this is negative 18. Okay, so this is position at, no, it's not. Never mind. Okay, just forget it. Just forget it. Okay, scratch that. All right, so anyway, I'm on a vertical number line, and at the end of this interval, at, I guess at time t equals 16, that's where I would be. Display distance from initial position. Yeah, that's my distance from my initial position. Okay. Alrighty, now the total distance traveled. Ooh. Okay, yeah, this is my distance from my initial position. Okay, wherever my initial position was, wherever I started out at, I am this far from it. in a negative direction. So I guess I'm this far below it, maybe. Yeah, that makes sense, I think. Okay, so now total distance traveled. It's extremely similar, except I've got to take the absolute value of the velocity function. So 2/3 t to the 3/2 minus 18 dt. Yeah, so part C, I didn't even read the directions, says set up an integral to find the total distance traveled within that time interval. And then it says we could use the calculator. So, to the calculator, Math 9, 0 to 16. But the absolute value button, guys, you go math and then you go over to number and then abs. Okay, that'll give you an absolute value function. So x to the 3/2 minus 18. Okay, so that's the total distance traveled. So it was going up, down, you know, definitely is, this is a lot greater than the displacement, which was the distance from our initial position. So you know it was moving around a lot within that interval. Okay, so within that time interval. So 179.4667, we'll say. All right, so that's the first example. Second example. This one. Okay, so this will bring in some stuff from the past. An object moving on a horizontal line has this velocity, 5 cosine of t, miles per hour, in the time interval 0 to 2 pi hours. A, find the time subintervals in which the object moves to the right and those in which it moves to the left. Well, guys, moving to the right and moving to the left, we've got to find where the velocity function is positive or where it's negative. If velocity is positive, we're moving to the right. If it's negative, we're moving to the left. So first, we've got to do a number line test, and first we've got to figure out where it's 0. So I'm going to take my velocity function. I'm going to figure out where it's 0. So I've got 5 cosine of t equals 0. All right, now my number line, I'm not going to do arrows at the end because I'm only concerned with this interval from 0 to 2 pi. All right, so I need to know where is cosine t equals 0. I divided both sides by 5. Well, if you imagine your unit circle, cosine's the x coordinate, so it'd be 0 here and here. So t is pi over 2, t equals 3 pi over 2. Those would be the critical numbers. All right, so that's where the particle is at rest. Or the object would be at rest there because velocity would be 0 there. So pi over 2, 3 pi over 2. All right, so this is the velocity number line. So I'm going to pick numbers in here and I'm going to plug it back into the velocity function and see if it's positive or negative. So you pick something here. Well, between 0 and 2 pi, cosine is positive. Between pi over 2 and 3 pi over 2, cosine's negative. And then on that interval, cosine would be positive. All right, so to answer their question, okay, the object is moving right for values of t between 0 and pi over 2, and then union 3 pi over 2 to 2 pi. And they're not asking us to explain why, but if so, you would say because on these intervals the velocity is positive. All right, and then left on this time interval. And if they asked why, you'd say because on this interval the velocity is negative. Okay, so that was sort of a blast from the past. I know we've done that before. So B, set up integral expressions to find the distance the object travels in each of these subintervals, and then evaluate these expressions without using our calculator. Okay, so for part B, remember from this front page that the total distance traveled will be the absolute value of the velocity function. So I've got 3 subintervals, 1, 2, 3. I want the total distance traveled on each of them. So on this first one, it's going to be 0 to pi over 2, and then absolute value of 5 cosine of t dt. All right, so I'll do this one first. Now, guys, this is equal to the integral from 0 to pi over 2 of just 5 cosine of t because, so let's say this, because cosine of t is greater than 0 on this interval. So this function that we're working with is completely positive on this interval. So the absolute value of it would be the same as its regular value because they're both positive. All right, so I could just drop those absolute value signs. And then this is equal to, all right, I'm going to do the antiderivative in there. And then I'll use the fundamental theorem of calculus because they don't want us to use our calculator. So constant multiple rule, I'll just take the constant multiple, which is 5, and I'll write it in there. And then the antiderivative of cosine is sine. All right. So the way this works is I just plug in that upper limit and I subtract what I get from plugging in the lower limit. And this is 5 times 1 minus 0. Okay, so that's the distance traveled. So it traveled, it was, on this interval, it was traveling right the whole time. And by the end of the interval, it had traveled 5 miles, right? Because this is miles per hour. So it had traveled 5 miles. Actually, let me say that, 5 miles. Alrighty, so now this second interval here, all right, I do the same thing, except I'm going from pi over 2 to 3 pi over 2, absolute value of cosine. And then this is equal to, okay, the integral over the same interval, but negative 5 cosine of t. And I'm going to tell you why in a moment, but think about that. Pause it if you want to figure it out yourself. Okay, but I'll say it right here. And that's because cosine of t is less than 0 on this interval. Guys, so what the input in the absolute value is negative. So if I were to just negate it, I'd end up with a positive value. So that's how that works. Okay, and then this is equal to, the antiderivative here is negative 5 sine of t, 3 pi over 2, pi over 2. And then when I plug 3 pi over 2, I get negative 5 times negative 1. And then when I plug in pi over 2, I get negative 5 times 1. So this is positive 5 plus 5, so 10 miles. So on this interval, it traveled 10 miles. It was going left, though. So it went right 5 miles, left 10 miles. And now we just have to do the last one. Actually, guys, in the interest of time, I won't do the last one. Okay, we'll just cut it off right there. Okay, so I think you get the idea. All right, now, use your answer to part B to find the displacement and total distance traveled in the time interval. Actually, this is probably worth it. No, never mind. Okay, we're going to skip C. I think it would have been worth it, though. And now D. Set up a single integral to find the displacement within that time interval, and we will use our calculator. Okay, so the displacement, so we're skipping all the way to D. Displacement on this time interval, it'll be the integral from 0 to 2 pi. And I put the velocity function in here, not the absolute value. That would give me total distance traveled. All right, and then I just use my calculator. I've got to be in radians. Math. No. How does this work? Mode. Yep, I'm in radians. So I go math 9, 0 to 2 pi, 5 cosine of x, and then all of this is with respect to x. Oof, jeez. Yikes. That's a small number. Set up a single integral to find the displacement in this interval. Use your calculator to evaluate the integral. Darn, that's so small. Jeepies. That doesn't seem right. That doesn't seem right at all. So we went... Just a minute. Right 5, left 10, and then right 5. Oh, okay, I guess this makes sense. Okay, wait a minute. So then this last one, sorry friends. Maybe this does make sense. It's just a very, very small, because the displacement would mean, okay, all right, I promise I'll go fast from here, but just a second. I think that it would have been worth it to find this last one. Okay, so the last integral would have been 3 pi over 2 to 2 pi. It's positive there. Well, anyway, I'll go 5 cosine of t dt. All right, so that's, I'm still on part C, I guess. Sorry, you guys. I just can't start over now. This video is too long. Okay, so math 9. Okay, so 3 pi over 2 up to 2 pi, 5. And then cosine. Okay, equals 5. Okay, so this makes sense to me now. Okay, so anyway, for part D, we did 0 to 2 pi, 5 cosine of t dt. All right, so this is part D, and this was like about 0. So it seems like, so the displacement, which is the distance from the initial position, we're almost like right back at the beginning, and that makes sense. Okay, so I just plugged it into my calculator, remember, and I got this number, which is a very, very small positive number. Well, this makes sense to me now because, okay, so I figured out by finding the third total distance traveled that, so on this interval we're traveling right 5 miles. And then on this interval we go left 10 miles and then again right 5 miles. So right 5, left 10, right 5, you end up right back at the beginning, okay? So that's good to know. So that's D. All right, and now E, set up a single integral to find the total distance traveled within that time interval. Now let's think about this, guys. What it should be anyway. If we go right 5, left 10, and then right 5 miles, if we go right 5, left 10, and then right 5 miles, that should be 20 miles total. All right, so let's see if our calculator will give that to us. So I want to go 0 to 2 pi, 5 cosine of t dt, but the absolute value of it. All right, maybe that should just be 0. Okay, so math 9. Sorry for the long video. 0. Okay, and then I go math. Okay, so this is 5 cosine. I'm hoping I get 20. Yes. Okay. Yes. That makes sense. So I really think that this should be 0, guys. The calculator was just like off a little bit. Okay, friends. Sorry for the long video. And I will see you tomorrow. Okay, bye-bye.